I invite Professor Howard Dittmer, I'm sorry if I'm pronouncing it wrong, and from DePaul University to present a code generation based on interface and controlled natural language input base.
Thank you very much. Yes, and he did very well. Probably much better than I've done with some of the other names. So yes, I'm going to take you a different direction. I mean, from the very large to the very small systems. So we're going to talk about code generation, particularly on end user applications, and we have done some interesting work here. So the background is that we're looking at programmer productivity. So we as programmers develop tools to make other people productive, but while over the years there's a lot of effort gone into different tools for programmers, very little of it has addressed actual code generation. So we've focused on what has been termed intelligence augmentation. We don't look to automate the entire process. We look to give the tool to the programmer to make them more effective, and to give them feedback, and not to simply generate a program, but to suggest and take some risks in the process, but then allow them to adjust from there. So we've developed a tool which we've termed CABERNET, which is a controlled natural language-based approach. And the goal is to increase programmer efficiency. We want to keep the syntax simple and flexible, English-like, but not verbose, and then to address the needs of all programmers, not just experienced programmers or inexperienced programmers, but the wide range. And to use a natural language-based solution, which is flexible and forgiving, and then use inference to fill in the gaps where the natural language description is not complete, and then to use programmer feedback to adjust, knowing that you're not going to be perfect in the natural language solution. The syntax in general is an outline-based syntax. It is very terse. We don't look for a lot of flowery language here, and the nomenclature is flexible. So we make a wide use of synonyms and thesaurus to try and assess what the programmer had in mind. And then, in the outline, each bullet has a limited context. So what we're able to do is we say, if we're going to interpret English language, we don't have to worry about the mixing of a mathematical statement with a search term, and have the interpretation be easy. And we based it on the Markdown markup language. And so you can see on the right there that here is a typical portion of a program. It's outline based, a little hard to read because of the text, but Markdown is nice in that we are now able to take that and render it so it's a much easier read. You generate it in this form, and then if you want to review your code, you have a much more visually attractive result. As I said, we make wide use of thesaurus. So you can see at the bottom, we have the categories of things like application names. You can call it an app, you can call it an application, you can call it a program, or screens. You can call them a scene or a window or a screen. And these are just simple selection. But the idea is that we can use available sources, web-based thesauri, other documentation to come up with other different names for the same type of concept, and then use that as a way of interpreting what the programmer has in mind. Traditional programs are imperative in nature. They describe what to do. Draw a box, put it in the middle of the screen. Recently, a lot of work has gone into moving in the direction of declarative, where you say, okay, I want a box in the middle of the screen. What we've done is we've taken declarative to the next step. We've taken a declarative type approach, but we're using natural language-based solution and then inference to try and discern the programmer's intent. We make broad use of templates and defaults to fill in the gaps where the programmer has been silent on different aspects of the program. As we talked about, we're processing a controlled natural language, so it's not a full sentence, but we use English-based phraseology. So you can see in the first line, here's a mix of programming symbols and English to describe a calculation. We take that and we tokenize it, break it up into the individual pieces, and then we look for objects. In this case, we say, oh, I look through here and I see some mathematical formulas, mathematical symbols. Perhaps this is a math statement. We don't know for sure, but we then look and say, okay, the things that aren't math, they aren't multiply, divide by a sign, a number. What are they? Are they in fact objects in my program? If they are, perhaps this is a math formula, and I can test. Can I take this and interpret it into a math formula? And you can see at the bottom that we've taken and said, bill amount is a field on my screen. Tip percentage is a field on my screen, and split is a term on my screen. I can make that into a formula, and you generate a mathematical formula based on that. So the whole idea is each bullet contains one context. You don't mix search and math, and because of that, it's easier to interpret. The context is encouraged to be terse. So if you're going to describe the color of an object, you just put the color. Or if it's text, you just say italics. And by making it limited, we know in the context that green probably means the color of the text. Width probably means the width of the field. For things that require more evaluation, like math statements or search statements, you contain only the information that is intended to cover that area of the program, and therefore it's easier to interpret from the English. And then once we interpret it, then we test that assumption. So we say, okay, if it's math, is there anything in this statement that doesn't make sense? Are there things that aren't a field? If it's like 90% interpretable, then we feed it back to the programmer and say, hey, here's what we got. Is this, are we interpreting this correctly? And what do I do about this piece that I don't understand? So the process is like this. You generate the CABERNET code, you take that and you tokenize it and store it as a JSON file. We inspect all the objects in the JSON file for synonyms. Are they one of the types of things that we look for? Perhaps a command, go to, or a mathematical statement. We fill in the gaps based on inference. What is the context and what things might be filled in there. We identify objects based on the context. Then we test the accuracy of each identification. Okay, does this all add up to a whole? If it does, fine. If it doesn't, then you provide feedback to the programmer. What am I missing here? So then we simplify the objects with natural language tools, as you saw earlier. A mathematical formula, we can take the English and put it into the result that is a mathematically evaluatable statement. And then we generate target code by applying templates. And the concept is that, okay, I'm going to write some iPhone programs, and I have a series of templates that embody how I want my programs to look. If I'm going to go into another area, I can have other templates, or I can have, if I change my style, my appearance, I can have other templates that are appropriate. And then we take it and we compile that interpreted code to the target part platform. We can generate from a given CABERNET program in Markdown, we can generate programs that run on Swift, Swift UI, Android, running on iPhones or Android phones. And so for some examples, some simple examples, here is a volume calculator. You can see on the left is the CABERNET code, which is very clean and easy to understand. 15 lines of code are interpreted to 133 lines of Swift. I've shown 31 lines here, but you can see the readability of one versus the other, and the result is the same program. Once again, if you look at Swift UI, which we talked about as earlier, is declarative. You can see that it is more readable, but there's still a lot of extra material in there that is repeatable. So things like the stack description to say how you align things. We just know, all right, if I have a label and a field, I'm going to put them on one line. And if it's not, you tell me about it. So you can see here, the program on the left, which is 15 lines of CABERNET, gives you a functional calculator with 3 input fields and a result and a calculation and some navigation buttons. And, you know, once again, you know, a tip calculator. Once again, simple programs, but 15 lines of code, whereas you have hundreds of lines of code to do this in traditional programming. You know, we see it as an opportunity to grow this based on search. So the intent is that the thesaurus and the solutions will be something that will be grown by searching APIs, industry documentation to generate the core templates and thesauri. And currently, we're able to generate iPhone programs in Swift or Swift UI, multi-screen applications, navigation, forms, calculations, including error checking. So things like, okay, I'm going to do some math. If I divide by something, I don't want to divide by 0. Okay, if I'm in a traditional programming language, I have to do a check for divide by 0. Those are things that you inherently know, and we can incorporate in the tool itself. Future, much more is possible. By learning from using search and target APIs, we can cover a wide range of applications. So that's my story, and I'm open to questions.
Thank you, Professor. Thank you very much. That example is really easy to understand, and thanks a lot. And from the forum, do you have any question to Professor? Yes, go ahead.
So one question is there any performance issues that you faced, or the way the structure is? Do you see any performance issues, etc., when we take this to the real systems?
No, I mean the whole point is this is a upfront interface. We generate native code. So from a performance standpoint, you're actually, when you're running it on the phone, you're running Swift or Swift UI code in this case, or in Android code. You know, you'd be running Android code. So at the end of the day, you're running the same program. It's a matter of how we generate it.
Okay, thank you.